what we're going to be talking about today are circuital laws. So this is still largely a review of what you guys covered in your freshman series. We're pretty much going to wrap things up that you learned as a freshman in our next class meeting. So the first thing that we're going to talk about today is Ohm's law. So way back in, I believe, the 1830s, there was a German physicist by the name of George Simon Ohm that performed a bunch of experiments. Okay? And the experiments that he performed had a setup similar to this. So he had a material under test that was a two-terminal, we can call it a network or whatever we want. I'm going to refer to this thing as a linear black box network. And by next Friday, we will have some idea of what that word linear means. And it was a two-terminal network, as I said. And connected to the two terminals of that linear network was an excitation source. Okay. I'm going to put a tilde here. So it doesn't particularly matter whether or not this source that we're using to excite this linear black box network is a voltage source or a current source. That doesn't have any bearing on Ohm's experiments. What he did was he measured the voltage drop across the terminals of that linear black box network, and he measured the current flowing through that linear black box network. And he found out that for the overwhelming majority of materials, there was a linear or proportional relationship between the voltage across the network and the current flowing through the network. Does this experimental setup look familiar to you guys? Because I made you do it at the end of the last class meeting. This is what your lab was. You had a network, you were measuring the voltage drop across it and the current flowing through it, and you should have gotten, when you plotted everything in Excel, a nice straight line, right? So your plot should have been something like this, where current I believe you guys were probably measuring in milliamperes, was on the vertical axis. Voltage V, measured in units of volts, was on the horizontal axis. And your plot looked something like this. What was the slope of your line? I think it was probably 0.2. Yeah. You guys did your lab reports and all that kind of stuff. Somebody look it up real quick. A lot of you did them on computers. Just tell me what the slope of your line was. What was that, Bree? I'm surprised by that. Oh, so that might be it. Okay, so that's probably why. So 2 and some change, so let's put this here. The slope was approximately 2 milliamps per volt. Okay. So that slope is what is commonly called the conductance G of a network. So the conductance is simply the ratio of the current divided by the test voltage. Now, there were a lot of questions from you guys and in previous years about what's supposed to be the independent variable and what's supposed to be the dependent variable in your graphs. So if we were to plot things with voltage on the vertical axis and current on the horizontal axis, we'd still get a straight line, or the slope of this particular line should have been about 0.51 volts per milliamp. And this slope is referred to as resistance. So resistance is defined as the ratio of voltage to current. Conductance is defined as the ratio of current to voltage. And so we can see that these two quantities are just the reciprocals of each other. So in practice, resistance is used as a quantity a whole heck of a lot more than conductance is. You don't really start seeing conductance measurements and stuff like that until you get into various aspects of things like transmission line theory and all that kind of good stuff, where the conductance is used to represent current leakage between your conductors in a transmission line system. So for the overwhelming majority of this class, effectively every day after today, anytime that you see a conductance, you should just take the reciprocal of it to turn it into a resistance, and then use all of the resistance techniques that we're going to develop in this class to be able to deal with it. Okay. For today, we are actually going to slightly pay attention to conductances. So the units of conductance are the Siemen with symbol capital S. That is simply the 1 amp per volt, and the units of resistance is the ohm, symbol capital omega. That is 1 volt per amp. So to hit you guys with some definitions, we can consider resistance to be a measure of how difficult it is to pass a current through a component or network, because we can very regularly represent an electrical network by its equivalent resistance, and we'll talk about that next class meeting. So from this definition, what I mean explicitly is the larger the resistance value, the harder it is to pass a fixed amount of current. Okay. And then conductance is just the opposite. It is a measure of how easy it is to pass a current through a component or network. All right, so what are resistors used for? some of you guys that were recently freshmen, you were asked probably on the second or third day of your engineering 120 class, you were asked to set up the following circuit. You had 5-volt output from your Arduino, commanded by a digital write high command. And then you had a resistor. By the way, this is the schematic symbol for a resistor. And then you had an LED. What was the purpose of that resistor? Walker.
It was this right here, otherwise it would be potentially short circuit the entire system because of the
So it wouldn't short circuit anything. We'll talk about short circuits here in a moment. So the resistor's purpose was to limit the amount of current that was flowing through that LED, because the LED can only handle a certain amount of current before it overheats and burns out, which is what Walker was referring to there. So resistors are used to limit current. And how they do that is they effectively just convert electrical energy into heat. That's all a resistor can literally do, is convert electrical energy into heat, okay? A resistor is not capable of storing energy. So since a resistor is not capable of storing energy, it is incapable of supplying power to a circuit. It can only absorb power, okay? So the reason why that's important is because we have this pesky thing called the passive sign convention that we talked about during our last class meeting that we need to obey, okay? So if I have a resistor R like so, and I define the voltage drop across my resistor with positive polarity on the left, which the terminal that has the positive polarity isn't particularly important, and my current I sub R is flowing into the positive polarity terminal, then Ohm's law tells us that VR will be equal to I sub R times R, right? And that's the Ohm's law that you guys all learned way back in your freshman class, right? V is equal to I times R. However, because we are doing that pesky thing of paying attention to polarities and trying to satisfy the passive sign convention, if instead we have a resistor R and things are set up such that the current is flowing into the negative polarity terminal, Ohm's law will now be expressed as negative I times R. And the reason why it has to be this way is because resistors can only absorb power, which means one of those two quantities, either the voltage or the current, literally has to be negative, okay? So that negative sign is fixing things so that it will be absorbing positive power, okay? So just to recap here, whenever we have current flowing into a positive polarity terminal, Ohm's law is V is equal to I times R. Whenever the current is flowing into the negative polarity terminal, V is equal to negative I times R. So effectively, whatever polarity terminal the current is flowing into tells us what sign Ohm's law is supposed to have in order to set things up correctly. Exact same rules would apply for conductances. Okay. So Walker just a moment ago mentioned the concept of a short circuit. So let's talk a little bit about that by exploring the relationship between the geometry of a conductor and the resistance of a conductor. Okay. So this is something that I believe, at least back when I taught the Engineering 120 series, this is a relationship that you guys were taught, where resistance is equal to rho E times L divided by A, where rho E is the electrical resistivity. This is a material property. So copper has one particular resistivity, silicon has another resistivity, all that kind of good stuff. This L is the length, and this A is the cross-sectional area of the conductor. So because the resistance depends on not only the material, but also the geometrical properties of the conductor, resistance is what we would call an isotropic property, meaning it depends on direction. So if we had a wire, let's say that we have a long section of wire, like so, where we're assuming that our current is flowing down the axis of symmetry of this wire so that we're not setting it up like some sort of jackass where the current is flowing into the top and out of the bottom of the wire. Let's calculate what the resistance of a section of wire should be. Okay? So I want to choose 22 gauge wire because that's what the wire that we have in this room for your hookups is. That's what you guys used in your freshman classes and all that kind of stuff. So let's pop over to Google here and let's look up the diameter of 22 AWG copper wire. So 0.0253 inches. All right, let's write that down. Let's also look up the electrical resistivity of copper. We'll do that in a minute. Resistivity of copper. 1.77 times 10 to the minus 8 ohm meters. All right. And just for the sake of argument, let's say that our length is something long, like 10 meters. Okay. So before we begin here, how long is 10 meters compared to the length of the wires that you guys have used in your projects to this point? Yeah, so the wires that you guys have used to this point are at best maybe 6 inches long tops. 10 meters would be in the ballpark of, I think, like 31 feet or something like that. So significantly longer. Okay, so let's calculate the resistance of this AWG number 22 wire. Okay. So we're going to have our electrical resistivity 1.77 times 10 to the minus 8 ohm meters times our length of 10 meters, and then our cross-sectional area. So because we were given the diameter, that's going to be what, pi squared over, no, pi over 4 times the diameter squared, is that right? Okay. So pi over 4, because pi r squared is the area of a circle in terms of radius, all right? Our diameter, 0.0253 inches. And then let's see, so there's 2.54 centimeters per inch. And then there are 100 centimeters per meter. And so I believe I'll wind up having meters squared in the numerator and meters squared in the denominator, canceling each other out. And so the only unit that's going to survive is that. So somebody that remembered to bring a calculator, tell me what number you get. Walker, you got anything for me? You don't, if you don't have your calculator out, somebody else can do it. You were just looking content, so I thought maybe you had finished already.
Nine, the one you said,
36x. Troy. 0.01386 ohms. Okay. Or we could call this approximately 13.86 milliohms. So my next question to you guys is, how does that number compare to the smallest what's up? 0.545, okay. So looks like more people got 0.545, so let's leave it as that. Oops. Okay, so half an ohm. Also seems reasonable. All right, so how does this number compare to the size of the resistors that you've used to this point? What's the smallest resistor that you guys have probably used to this point? In the LED circuit that we described up here, I believe you were expected to use a 200 ohm resistor, which is, I believe, the smallest one that was in your kit. And the reason that you used a 200 ohm resistor is because that would give you the brightest light out of your LED. So a 200 ohm resistor is about 400 times larger than the resistance of a wire that is 10 meters long. If your wire was only a few centimeters long, you just move that decimal point, or you'd start adding more zeros, I guess, in front of that 545, right? Very little resistance in a wire. So for all intents and purposes in this class, we are going to treat the resistance of a wire as if it were zero. So all wires act like short circuits, okay? So a short circuit is an element where we literally have a wire connecting 2 points. The resistance of this thing, we are going to treat it to be 0 ohms. It's not really 0 ohms, but for the purposes of this class, we're going to call it 0 ohms. And thanks to Ohm's law, if the resistance is 0 ohms, what does the voltage drop have to be across a short circuit? 0 volts. So this actually explains why we're able to treat all points along a wire as the same node, like we did on our very first day of class when we were defining nodes and all that kind of good stuff. If there's no potential difference between exact same node. Okay. Now on the opposite side of the spectrum, we have an open circuit. So an open circuit can really be thought of as the absence of a conductor. Okay. The resistance of an open circuit is infinitely large for the purposes of this class. And because the resistance is infinitely large, Ohm's law tells us that the amount of current flowing through an open circuit has to be 0 amps. Now, this is just a simplified model of an open circuit, okay? Just like our short circuit is a simplified model for a wire, right? A wire has some amount of resistance. We calculated it, very, very small. An open circuit also has some amount of resistance, very large, and it's typically associated with the dielectric breakdown voltage, meaning how much voltage per unit meter you have to apply across a gap or something like that to cause the air or whatever medium is between the two open terminals to literally break down and start conducting energy, right? So you will, if I were to take a plug and not quite plug it in so that there's just a very, very small gap between the prongs of the plug and this receptacle, we'd start seeing a bunch of sparks and all of that kind of stuff because the distance is one of the determining factors for when you're going to hit dielectric breakdown, right? So if you put a conductor, see it arc over and conduct. The more energy you have, the larger that distance will be, which is why there are all those nice signs around power substations and all that kind of stuff saying, stay the hell away, risk of arc flash. It's because the energy is so high that the arc, instead of going over a millimeter or two, will go meters, hit you and kill you, okay? So.
Like a fork in a microwave, with the metal conductor and has.
That's a different bag of cats. That being said, don't ruin anybody's microwave by doing this, but if you throw a LED into a microwave, it'll light up because the wavelength of the induced voltages and currents is similar to the wavelength. Yeah, so anyway, don't do it. You'll ruin a microwave. It'll potentially break the microwave as well because of the way magnetic fields work. So my PhD advisor did. All right, so we've talked about resistance, we've talked about conductance, we've talked about open circuits and short circuits. We've defined Ohm's law for really both cases of the passive sign convention. Does anybody have any questions, comments, or concerns about Ohm's law before we move on to the other circuit laws that we're going to deal with for today? All right, so the next one that I want to talk about is Kirchhoff's voltage law. So we touched on Kirchhoff's voltage law very briefly in our last class meeting. Does anybody remember what Kirchhoff's voltage law, or KVL, says? So the sum of the voltage drops around any closed path must equal to 0. I'm going to underline closed path because we're going to talk about that here in a moment. All right. So before we work some examples here, why does the sum of the voltage drops around a closed path have to equal 0? Might be an odd question. Remember what we talked about in Monday's class with respect to voltages. Anytime we have a voltage, we're looking at a transfer of energy. Well, if we start our path at one point and end at the same point, we are in a conservative system. So effectively, we're saying the potential difference between this point and the exact same point has to add together to 0.
So if it wasn't there, would that almost be like perpetual energy? If you're putting energy back into the loop that wasn't there?
Exactly right. So somewhere along the line, we would have had to create or destroy energy in order to make this not 0. So Kirchhoff's voltage law is the law of conservation of energy for circuits. Really all it is. When we get to Kirchhoff's current law here in a couple of minutes, that's the law of conservation of charge as applied to circuits. All right, so let's look at a quick example here, right? So in its most simple form, Kirchhoff's voltage law is used to determine unknown voltages in circuits when we know other voltages, right? So let's say for the sake of argument that we have a 3-volt source, a resistance, a 9-volt multi-cell battery pack, and then let's say a 4-volt source down here. And what we are trying to find is the voltage drop across this resistor. Let's call it VR. Somebody tell me if we want to find the voltage with the positive polarity on the left or the positive polarity on the right. Left. Okay, positive polarity on the left. Okay. So how we would apply Kirchhoff's voltage law to this system is we would assume a direction, okay, that we're going to follow around. Typically, either clockwise or counterclockwise, it does not matter which choice we make, we're going to get the same result either way. I typically choose clockwise, so I'm going to indicate that like this. One way to think about this is that there might be some current flowing in this circuit. And so we're just going to follow the current around this path to see what happens, okay? So if we chose a clockwise path to follow, I like to start at the bottom left-hand corner. And if I see the negative polarity terminal first, I give that term a negative sign. And if I see the positive polarity terminal first, I give that term a positive sign, okay? So starting at the bottom left-hand corner and going up, the first thing I see is the negative polarity terminal of the 3-volt source. So I would have negative 3 volts. Then I see the positive polarity terminal of that unknown voltage VR. Then I see the negative polarity terminal of that 9-volt battery pack. Then I see the positive polarity terminal of the 4-volt source. And now I'm back at the same node I started from, so I am closed my path. So I set this equal to 0, and then I'm just going to rearrange and solve for VR, right? So that would look like VR is going to stay on the left-hand side of the equal sign. I'm going to move that 9 volts over. I'm going to move the 3. And so 9 plus 3 minus 4 is 8 if my mental math is correct. So the voltage drop across that unknown resistor with positive polarity on the left is 8 volts. That is how we're going to apply Kirchhoff's voltage law in this class. If we had chosen a counterclockwise path around this loop, right? So let's do this one in green. Okay. So let's say that we went this way instead. Let's just see, for the sake of argument, if we get the same result. Okay. So going counterclockwise around this loop, the first thing we would see is the negative polarity terminal of the 4-volt source, then the positive polarity terminal of the 9-volt battery pack, the negative polarity terminal of our resistor voltage, the positive polarity terminal of our 3-volt source, set this equal to 0. I'm going to move VR to the other side of the equal sign. So I have negative 4 volts plus 9 volts plus 3 volts is equal to VR. Negative 4 plus 9 plus 3 is once again 8 volts. So it's impossible to pick the wrong direction when applying Kirchhoff's voltage law. As long as you're consistent with anytime you see a negative polarity terminal first, you give it a negative sign. And anytime you see the positive polarity terminal first, you give it a positive sign, you will come up with the right answer. The direction you choose is completely and utterly inconsequential. All right, so this is simple application of Kirchhoff's voltage law, quite boring. Now, let's see what we can do if we were to include Ohm's law with Kirchhoff's voltage law. Just realized I forgot to talk about something having to deal with resistance and conductance, so we'll circle back around to that in just a moment. All right, so this is a circuit that I put on a test in this class last year. So we have a 13-volt source, (15-ohm resistor, (7-ohm resistor, a 9-volt source, we have a 12-ohm resistor, IX, and a 13-ohm source like, 13-ohm resistor like so. And what I want us to find, oh, and I need to define IX as well here. So I'll choose to have IX flowing in this direction. So I want us to find the power supplied by the dependent source. So what we are going to do is we are going to apply Kirchhoff's voltage law around this circuit. This is an example of what's called a single loop circuit, where all of the different elements are connected to each other in series, so that it forms just one single loop around the circuit. And any time that you see a single loop circuit, your default analysis technique should be Kirchhoff's voltage law, probably in combination with Ohm's law. Okay, so anytime it's just a single loop, KVL is going to get you practically all of the information that you want about the circuit in a step or two. So I'm going to define some voltage drops across these various resistors. So let's say that the voltage drop across this 15-ohm resistor, let's call it V15, and let's put it positive polarity on the left. And let's say that the voltage drop across the 7-ohm resistor is V7, and just for the sake of argument, let's put the positive polarity terminal on the right. For the 13 ohm resistor, let's put positive polarity terminal on the right. And for the 12 ohm resistor, let's put positive polarity terminal on the left. Okay. So now every single element in this circuit has some voltage associated with it. Okay. I'm going to choose to follow that current IX around its clockwise path for this circuit. Starting at the bottom left-hand corner, what should my first term be? So minus 13 volts, the minus sign because we see the negative polarity terminal first. All right. Then we see what? Plus V15, okay. Then what? Minus V7, okay. Then what? Minus 9 volts, okay. Then what? Then what? Minus 8 IX, okay. And then what? Minus V12, sorry, I've dotted that 1, is equal to 0. Okay, so by applying Kirchhoff's voltage law to this circuit, we have come up with one equation that has 1, 2, 3, 4, 5 unknowns, okay? Less than stellar, okay? But one great thing about a single loop circuit is that the current flowing in that loop is constant and shared by all of the different elements, right? So what we are going to do now is we are going to figure out how to express every voltage drop across a resistor in this circuit in terms of that current IX using Ohm's law, okay? And then we're going to be able to substitute all of those Ohm's law relationships into our KVL equation, and we will wind up getting a single equation with a single unknown variable, the current IX. So how do I express the voltage V15 in terms of the current IX? 15 ohms times IX, absolutely right. What about the voltage V7? Troy, what did you say? Negative 7 ohms times IX. So Christina was asking if we need to make this Ohm's law equation negative. And to answer that, we simply look. Is the current flowing into the negative polarity terminal or the positive polarity terminal? It is flowing into the negative polarity terminal, so we need a negative sign. What about V13? 13 ohms times IX. Brody's brother, Carson, maybe? For V13, do I need a negative sign or not? I don't, right, because IX is flowing into the positive polarity terminal, right? And then lastly, V12, what's going on with V12? Mackenzie, can you help me out? So why do you say the current's flowing into the positive? On that bottom portion, it's going to be flowing from right to left, so it would hit the negative polarity terminal first there. Yeah. All right. Law relationship, and we wind up getting a single equation only in terms of the quantity IX. So let's go ahead and substitute things in here, right? So we're going to have negative 13 volts plus V15, which was 15 ohms times 7 ohms times IX minus 9 volts plus V13, which was 13 ohms times IX minus 8IX minus V12, where V12 was negative 12 ohms times IX. Set this equals 0. So let's lump some things together. It's 13 plus 9, so that's going to look like 22 volts, I believe. And then I'm going to put all of my IX terms on the left-hand side. So I'm going to have 15 minus negative 7, so 15 plus 7 is 22. Add 13 to that, so that's 35. Minus 8 is going to give me 27. Plus 12 is going to be 39. Actually, let me put this as 39 ohms IX, so we're not playing fast and loose with the units. Now, one thing that you guys may be slightly concerned about here. So the 15 ohm resistor, the 7 ohm resistor, the 13 ohm resistor, the 12 ohm resistor, I added all those together. I also added that negative 8 IX in there. Is that okay? Well, sure. Why is it okay? Because we have a current controlled voltage source, right? So the units on that quantity 8 are measured in volts per amp, which is the same as the unit of resistance, an ohm. So that's why I can add those together. Even though it's not technically a resistance, it still has that same linear relationship between voltage and current as all of the resistors do. So now I could rearrange this thing and see very easily that IX is 22 volts over 39 ohms, which is the same as 22/39 of an amp. Am I done? No, because I asked, what's the power supplied by the dependent source? Now that I know that current, how will I find the power supplied by that dependent source? So 8 times IX is the voltage, because that's a voltage source, but power is voltage times current, okay? So I need, so 8 times IX, which is the voltage, times IX, which is the current. Do I need to add a negative sign? Supplied, so I do not, right? So to calculate supplied power, it's just I times V if the current is flowing into the negative polarity terminal. And our current IX is indeed flowing into the negative polarity terminal of that dependent source. So just 8 times IX, or as Christina suggested, 8 IX squared. So sure, I have a calculator down here somewhere because I can't do 22 over 39 squared in my head. Oh, no, apparently I don't have a calculator on me. All right, so somebody give me a number for that. 1408 over 39 is good enough for me. Watts, absolutely right. So while we have this example problem up, I want to look at one more quick thing here, okay? So we learned in Monday's class meeting that voltage is just the potential difference between 2 points in a circuit. And we learned that we can apply Kirchhoff's voltage law around any closed path. So for some things in this class, let me do this in, let's say, green. We might have something like this, where we're trying to measure the voltage across an open circuited set of terminals. Okay? Students, for whatever reason, don't seem to like it when I ask you guys to do this, and I really can't figure it out because this is just like if we hooked up a multimeter between those 2 points in the circuit and where I was asking you to predict what the multimeter was going to give you. So a measurement like this is absolutely fair game. I think the things that students don't like about this is part of our closed path can't carry current because it's an open circuit. But does Kirchhoff's voltage law care about whether or not current is flowing? Absolutely not. Kirchhoff's voltage law is just the sum of the voltage drops around a closed path. So if we were trying to find this voltage Vx, there are two different paths that we could use. Each would give us the exact same answer. So we could choose this path, and the direction is unimportant, or we could choose this path. Now that we know that current Ix, all of those voltage drops except for Vx are known quantities, right? So for this one, I would probably choose that left-hand path because it's got the least number of terms in it, which means it's the least opportunity for me to make a silly mistake. So if I were trying to find Vx, I would write my KVL equation around that left-hand path. So that would look like negative 13 volts plus V15, which we know is just 15 ohms times Ix. So let's put 15 ohms times Ix was 22 over 39. Plus Vx. And then we would have minus V12, where V12 was negative, so it would be plus 12 ohms times that same Ix, 22 over 39 amps is equal to 0. Solving for Vx, we would have 13 volts minus 15 plus 12 is 27 ohms times 22 over 39 amps. And that's going to be a number. Once again, I forgot a calculator, so somebody else tell me what that is. Minus 29 thirteenths of a volt. Okay. So asking you for the voltage drop in the middle of a circuit or something like that is absolutely fair game. It's just applying Kirchhoff's voltage law like we've done before in a slightly different context, right? Okay. All right, so before I go back and talk about the power relationships for resistors and conductances, because I forgot to do that, does anybody have any questions on Kirchhoff's voltage law? Oh, so why did I choose that way? To make it confusing. To force you to have to realize that sometimes Ohm's law is going to require a negative sign. So when you do these by yourself, the obvious way to set a circuit up and introduce the least number of negative signs would be to make it so that the current is flowing into the positive polarity terminal whenever possible. But because I am mean and a jackass, I chose some of them of the opposite polarity to try to trick you guys. Yeah. Absolutely. If you can get your hands on a dependent voltage source, which would be some sort of transistor based thing. But yeah. Yes. So when I'm talking about right here, so I have negative V12 but V12 already has the negative sign, so those two negatives cancel each other out to make a positive. Yep. Yep. Any other questions? Yes, Walker.
Never, how can you tell which side?
You can't, because it doesn't matter for a resistor. So you just arbitrarily assign one to be the positive polarity terminal. Yeah, so like a battery. We don't define it. For inductors, because it doesn't matter, we don't define it. For most capacitors, because it doesn't matter, we don't define it. Some capacitors, called electrolytic capacitors, are polarized, meaning that if you connect the voltage the wrong way, it will actually cause the capacitor to burst. And so on those, it is clearly defined what the positive polarity terminal is. For a diode, the polarity of the voltage across the diode matters a whole heck of a lot. So the negative polarity terminal is always identified with a silver stripe so that it's letting you know which side is negative. For an LED, the long leg is positive, the short leg is negative because the polarity matters. So effectively, if the polarity matters, there will be some sort of indication. If it doesn't, there won't be. So for this class, a lot of what you're going to be doing is deciding which polarity of this particular component should be positive, and which direction do I think the current is flowing. It does not matter what you choose, as long as you're consistent with applying the circuit theory, the math's going to work out correctly to give you the answer that you need. So I typically do it that way because I know that I screw up when I have lots of negative signs in there mixing things up. Yeah, so I usually choose to try to set things up such that my current is flowing into the positive polarity terminal of practically everything I can make it flow into, so that I don't get a bunch of spurious negative signs which hurt my brain. So any other questions before we go back to talk about power relationships and then move forward to talk about Kirchhoff's current law? All right, at some point I'll probably have to start bringing notes. Okay, so our power relationships, and sorry for missing this earlier, we have a definition for Ohm's law here. So let me just sneak these relationships in here. So for a resistor, our power is always going to be I times R. Excuse me, I times V. And then using Ohm's law, we could express this then as V squared over R, or I squared times R. So that's just simply substituting Ohm's law into our power relationship. For conductances, it's still going to be I times V. So it's going to look like V squared times G, or I squared over G. Okay. These are just shorthand notations for determining the power, because we know that for a resistance or a conductance, it's always going to be absorbing power, which means since we're squaring the voltage or squaring the current, the polarity of the voltage doesn't particularly matter, or the direction of the current doesn't particularly matter, because once we square it, we're going to get the same number either way. Okay. So sorry for forgetting. Current law. All right, so there are realistically 3 different ways to express Kirchhoff's current law. They all pretty much mean the exact same thing, okay? So what I'm going to do is I'm going to draw a little portion of a system here, okay? So I'm going to start with some central node point, and let's say that we have a wire that's part of a greater circuit, another wire, also part of the same circuit, yet another wire, wire, and wire. And let's define our current I1 to be flowing into that node. I2 will flow out. I3 will flow out. I4 will flow in. I5 will flow out. So our first formulation for Kirchhoff's current law is probably the one that you guys are the most familiar with, which states that the sum of the currents entering a node must equal the sum of the currents exiting a node. So in this case, we would say, well, I1 is entering, so let's put that on one side of the equal sign. I2 is exiting, so that should go on the opposite side. I3 is exiting, so that should go over here to the right. I4 is entering, so it should be over here to the left. I5 is exiting, so it should be over here to the right. And there's our Kirchhoff's current law relationship. All of the currents that are entering the node are on one side of the equal sign. All of the currents that are exiting the node are on the other side of the equal sign. So everything is balanced. Okay. So like I said, that's probably the formulation that you guys are most familiar with. Okay. Now let's talk about the other two formulations. So another way to express Kirchhoff's current law is simply the sum of the currents entering a node must equal to 0. So this all of our currents, but I1 is entering, so it's going to get a positive sign. If I2 is exiting, then negative I2 is entering. So we would have plus minus I2 minus I3 plus I4 minus I5 is equal to 0, which is mathematically exactly the same relationship we got for formulation number 1 if we moved all of the terms that were on the right-hand side of the equal sign over to the left-hand side of the equal sign, okay? So they're the same damn thing, it's just phrased slightly differently or from a slightly different perspective. And then our third formulation is the exact opposite. The sum of the currents exiting a node must equal to 0. I hear whispering. I am fine with whispering. I am wondering if there is a question that you would like to ask of me, because I hope that I am not such an off-putting jerk that you guys are scared to ask me questions about stuff. That should be exiting. So in this particular instance, a current of negative I1 is exiting. So we would have minus I1. I2 is exiting, so that's positive. I3 is exiting, so that's positive. I4 is entering, so we would do negative. I5 is exiting, so that's positive, and set it equal to 0. And this expression is just the expression above, except everything is multiplied by a factor of -1 because we're looking at things from the opposite direction. And anytime we change the direction on a current, we're just multiplying by a factor of -1. So all three of these mean the same damn thing, okay? So this begs the question, well, which one should I use? The short answer is whichever one you're most comfortable with. The better answer is whichever one you're most comfortable with until you learn nodal analysis and then number 3. So nodal analysis is a very, very powerful circuit analysis tool that I've mentioned before that we are going to be learning, I believe, next Friday. And in order to get a whole bunch of, or excuse me, in order to avoid getting a whole bunch of random negative signs, it's easiest to sum together all of the currents that are exiting the node and set them equal to 0 in order to set up our equations with that particular method. It's not required by any stretch of the imagination, but it is much, much easier. So I typically default to number 3, or formulation number 3 of Kirchhoff's current law here, just because I'm so used to having to apply nodal analysis to various circuits and things like that. So in the short term, whichever one works for you, works for me. In the long term, you probably want to get used to using formulation number 3 here. Okay. All right, so let's now work a couple of quick example problems illustrating how to employ Kirchhoff's current law. So let's start with something fairly straightforward. Let's say that we have a current source that is 4 amps connected in parallel to a resistor connected to 2 amp source connected to a 5 amp source like so. And we're trying to find the current flowing through the resistor. Somebody say up or down? Up, okay. So here is our resistor current that we're trying to solve for, okay? So this is an example of a single node pair circuit. And in a single node pair circuit, all of the elements are connected in parallel. So whenever you see a single node pair circuit, your default analysis methodology should be Kirchhoff's current law, okay? And then probably also Ohm's law with it when required. All right, so we need to figure out 2 things here. The first thing that we need to figure out is which formulation of Kirchhoff's current law we are going to use. Are we going to use number 1, number 2, or number 3? Emily, pick one. Number 2. All right, so we're going to do KCL number 2. At the top or bottom node. I'm running out of people's names that I remember. Wolf Creek shirt guy. Sorry, what's your name? Harrison. Harrison. Are we going to do this at the top node or the bottom node? At the top node. Okay. Harrison. All right. So we are going to apply KCL at the top node, where we are trying to find, where all of the currents that are entering the top node will get a positive sign, and all of the currents that are exiting the top node will get a negative sign because we're using formulation number 2. Okay. So let's just work our way from left to right through this circuit. The 4 amp source on the left, is it entering the top node or exiting the top node? Entering. So it should get a positive sign or a negative sign? Positive sign. All right, so 4 amps. Now we have our resistor current, IR. Is it entering? Positive. The 2 amp source kind of in the right middle, is that entering the top? The 5 amp source on the right, is it entering the top node or exiting the top node? Exiting, so it should get a negative sign. Now we can rearrange things, so we'll put IR on the left-hand side of the equal sign. I'm gonna move the 4 amps over. I'm gonna move the 2 amps over. I'm gonna move the 5 amps over. So -4 minus 2 is -6 plus 5 looks like -1 amp to me. So it's -1 amps up or +1 amp down. So that's a way, or example using Kirchhoff's current law, formulation number 2 at the top node. If we used any other formulation at either the top or the bottom node, we'd still wind up getting the exact same result. Walker, you had your hand up. What's up? Yes. I just have terrible penmanship. Yeah. So KCL formulation number 2 at the top node. All right. So we can also use Kirchhoff's current law in combination with Ohm's law in order to find out the voltage drop across a parallel network as well. Okay. So let's do something here. Somebody give me a resistor value between, I don't know, 10 and 25. 15. Somebody give me another resistor value between 10 and 25. 11. All right. Somebody give me a value for this current source that isn't 3. 4 it is. Walker called first. So for this particular problem, I'm once again going to ask about a power related quantity. So let's figure out the power absorbed by the 15 ohm resistor. Okay. Yes, ma'am. So we'll figure that out. It's probably going to wind up being a small amount of current, but it's not going to be 0. If I had made that right-hand source 3 amps, it would be 0, which is why I said any number but 3. Yeah. All right, so we are going to solve this circuit using Kirchhoff's current law and Ohm's law. So we need to arbitrarily define a couple of things here. First, we need to define directions for our current flowing through our 15 ohm resistor and the direction for the current flowing through the 11 ohm resistor. So tell me which one is up and which one is down, if either are up or either are down, whatever. Both of them up. Okay. So let's arbitrarily choose this to be I15 ohms and this to be I11 ohms. All right. What's your name? Ian. Ian, should the polarity of the voltage drop across all these things be positive polarity on top or positive polarity on bottom? Pick one. Positive on top. All righty. So I'm going to call this voltage Vx. And because all of these elements are connected in parallel, they all share this exact same voltage Vx. Okay. So now let's move along to applying Kirchhoff's current law. So which formulation are we going to choose? Number 1, current flowing in equals current flowing out. Number 2, current entering a node is equal to 0. Or number 3, current exiting a node is equal to 0. Number 3. All right. So KCL number 3. And are we going to apply this at the top node or the bottom node? Bottom. All right. So any current that is exiting the bottom node will get a plus sign. Any current that is entering the bottom node we'll get a minus sign because of the formulation of KCl that we're dealing with here. All right, so once again, let's start from the left to the right. So the 3 amp source, is it entering or exiting the bottom node? It is entering the bottom node, which means it needs to get a negative sign, absolutely. So negative 3 amps. Then we have the current I-15. Is it entering or exiting the bottom node? Exiting the bottom node, which means it gets a positive sign, absolutely. I-11 is also exiting, so it'll get a positive sign, and the 4 amps is also exiting, so it will get a positive sign. All right, so we have 1 equation and 2 unknowns. Because this is a single node pair circuit and the voltage is shared, we can use Ohm's law to express those resistor currents in terms of that voltage Vx, and we will wind up getting a single equation, single unknown system to solve. So, Hojun, using Ohm's law, what should my current I-15 ohms be in terms of the voltage Vx? All right, so Vx over 15 ohms. Is that current entering the positive polarity terminal or the negative polarity terminal of the voltage Vx? So that means I need a negative sign on my Ohm's law relationship, okay? Person sitting between Christina and Jacob, whose name I can't remember, I'm sorry. Jeremy. What should my Ohm's law relationship be for I-11 in terms of Vx? Yeah, except replace the 15 with an 11.
Yeah.
So negative Vx over 11 ohms, absolutely. All right, so if we substitute that in, so let's do that directly here, we're gonna have negative 3 amps plus negative Vx over 15 ohms plus negative Vx over 11 ohms plus 4 amps is equal to 0. So let's move some things around here. So the 3 amps, negative 3 plus 4 is going to look like positive 1 amp on the left-hand side of the equal sign. And then I'm going to have Vx times 1 over 15 ohms plus 1 over 11 ohms, which means ohms over 15 plus 11 ohms. And I did that by doing algebra that I've done a million times really quickly. If you want me to step by step you through why it looks like this on the right-hand side, I'm happy to do it. Yep. Yep. You could also just divide, so 1 amp over 1/15 plus 1/11, but I'm lazy. Yeah. So somebody throw this into a calculator and tell me what's what, because I don't see 165 over 26. I can't do in my head. Oh, well, actually, it could just be that, right? 165 over 26. Oops. 15 times 11 is 165, right? All right, so we have figured out what Vx is, positive polarity on top. So what we were trying to solve for is the power absorbed by this 15 ohm resistor. How do we get that? So I'll give you a hint. This is one of those relationships that I accidentally skipped over and we had to go back to, right? So because I know the voltage drop across my resistor, I can simply use V squared divided by R to give me the power. If I were a glutton for punishment, I could introduce an extra step and find the current, and then I could use I squared times R or I times V. Either way would wind up working, but because I'm lazy, and if I only need to know the voltage and the resistor value, that's the one that I'm going to use because that's the information that I have available. So this would be Vx squared divided by 15 ohms. So 165 over 26 volts squared divided by 15 is a number. Okay, so this voltage Vx is common to every element in this circuit. So every single element has a voltage Vx across it. So I could put Vx here, positive polarity on top. I could also put Vx here, positive polarity on top like so. And the current is flowing into the negative polarity terminal, which means I need a negative sign. I'm going to answer that question probably 3 to 5 times a day for the next 2 weeks, so don't feel bad for asking. So great question. So Christina just asked, what happens if we apply Kirchhoff's voltage law to a system like this? So the short answer is that regardless of what loop we apply, so let's go around this loop right here, right? So we would see the negative polarity terminal of Vx first, then we have a short circuit, then we see the positive polarity terminal of Vx, then we hit that other short circuit is equal to 0, which means negative Vx plus positive Vx is equal to 0. Of course it is. So that effectively means everything has the same voltage because regardless of what loop we choose or what path we choose, we're going to get the negative voltage plus the positive voltage is equal to 0. Absolutely, because the voltage drop across that current source is still Vx positive polarity on top. Yep, so there is a voltage drop across that current source and it is whatever Vx is. Absolutely, yeah. So regardless of the path that we choose, whenever we have elements connected in parallel, we will always wind up with the same voltage drop over both of the elements or however many elements there are in parallel. If we apply Kirchhoff's current law to things in series, we'll see that they have to carry the same amount of current flowing through them because there's nowhere for current to branch off, right? So when elements are connected in series, they have the exact same current. When elements are connected in parallel, they have the exact same voltage. And that is a direct consequence of Kirchhoff's current law and Kirchhoff's voltage law, respectively. All right, any other questions for me? Yes, sir. So if we had put just one of them arbitrarily with a negative polarity on top. So let's say, for example, here, that we called this voltage Vy, right? So for this relationship right here for I11, oh, sorry, and that should be a positive polarity there. We would wind up getting I11 ohms is equal to Vy over 11 ohms, right? But we can see by inspection that Vy is equal to negative Vx because it's the same potential, it's a potential difference between the same two nodes, but they're of opposite polarities. So it would still wind up being literally the exact same numbers. Any other questions? Yes, sir. What do you mean how I maintain units? I typically use units in literally all of my calculations. I'm not the type of person that tacks them on at the end. I start with them and I stick with them the whole way through. So yeah, after we wrap things up, kind of show me an example, I guess, because I'm not quite understanding the question. Any other questions? Yes, ma'am. Sure. So when we were writing this first equation, three is saying the sum of the currents exiting a node must equal to 0. So that means every current that is exiting the bottom node is assigned a positive sign, and every current that is entering the bottom node is assigned a negative sign. So if we look at our expression here, this 3 amps of current is entering the bottom node. So that's why it got a negative sign. This current I-15 is exiting the bottom node, so we gave it a plus sign. I-11 was exiting, so we gave it a plus sign. 4 amps was exiting, so we gave it a plus sign. Did that clarify? All righty. Any other questions? All right, well, I've ranted for, holy crap, 100 minutes. I mean, I did get 10 minutes late of a start. So you guys have about 12-ish minutes or so to work on the in-class assignment. If you have any questions about anything, I would be more than happy to answer.